Hello, my name is Martin and I'm software developer at g.tec. I'm mainly working on the Unicorn brain interface, and I'm going to show you the hard and software interfaces a bit for this device and give you a short introduction into the signals you can acquire with it, and show you the software framework a bit. So this is the Unicorn system. The system was designed to be operated out of the box, so you get the whole BCI within the box. You can see an amplifier on the picture. You can see some electrodes, an electrode cap, gel, a syringe, and a computer. That's everything you need to start with BCI research and applications. And this is the amplifier. So all the electrical signals are digitalized with this amplifier. You can see it has 8 electrode leads. That means we can acquire data from 8 electrodes. We also have a maker version of the Unicorn system. So you can buy the PCB if you want to build your own enclosure or build your own mechanical PCI. So if you want to do something like this, you can use the Unicorn naked. And here are some examples what people already built with the Unicorn naked. There's Robert Ostenfeld, who is a very famous researcher in the field of PCI. And he built his own cable connectors with the Unicorn naked, his own electrodes and so on. And it's really nice to see that people are using the system and building their own stuff. And here's a demo that we've made a while ago, where we made a 3D printed case and used it for different applications like ECG and EEG recordings. The Unicorn is used by a lot of institutions at the moment. Here's just a couple of research institutions and hospitals that you can see, museums. And these are the key specs of the Unicorn system. As mentioned before already, you can measure EEG from 8 channels, and we have a resolution of 24 bits. That means we can measure very small currents with very small amplitudes. And that's what we need for EEG. And we apply some strategies to achieve this, like a very high oversampling rate. That way you can get top quality EEG data. Another special thing about the Unicorn system is that we have hybrid electrodes. You will see that a bit later. Hybrid electrodes mean that you can use them in dry or in gel applications. So if you're sitting alone in your room and you're not moving much, then you can use the PCI with dry electrodes. Just apply the PCI and don't use any gel or anything. And you can work with it right away. But if you're moving a bit, or if there are a lot of people and you're in a crowded room, then you might want to get some better EEG signal quality, and that's when you would also add some gel. And with the hybrid electrodes, you can do both within one system without any hardware change. That's pretty convenient. So for the Unicorn, we place the electrodes all over the cortex. For the most common BCI experiments, we have some electrodes on the visual cortex, back of the head. And we have some electrodes over the sensomotoric cortex, so you can do motor imagery experiments. And we have an electrode over more close to the eyes, so you can also measure some eye blinks, EEG, and other physiological signals. Or some emotion stuff is also more in the front of the cortex. And we have the CZ electrode, so you can measure a perfect earpiece. Besides the hardware, we also have a wide range of software tools, ranging from API interfaces to finished applications. So there should be a lot of tools available that you can use in the hackathon. And here's the the amplifier again, and here you can see the 8 electrode leads and the hybrid electrodes on top. You can see the specific shape, so they can pass through the hair and touch the surface of your skin. And you can see that there's a hole in the middle of the electrode. That's where you can put the syringe in, and for some occasions you might want to add gel in there. That's a more detailed view of the electrode again. So you can see the electrode is completely passive. You can detach it after your experiment and throw it into water, so nothing is damaged there. If you use gel, you might want to use that to do that, to clean it again afterwards. You can see that it's simply slided onto the electrode clip, and that's how you assemble the device. But we will see that later. And here are some examples of applications that have been done. We worked together with some makers. So in this case, we built a gin tonic robot, as Christoph already mentioned before, for the Robo Exotica, a cocktail robot exhibition. We worked together with some digital artists like Alex Guevara, who made some very nice visualizations from EEG biomarkers. We've used the brain-computer interface to control robots, for instance. You can see that example here, or we control the digger and the Zero robot, but we control many different robotic devices so far. And then the bottom right, you can see the Unicorn project from Anouk Wiebrecht. That was actually the start for the whole Unicorn project, because it was the first project that was more outside of the medical range, and we saw that we need a more user-friendly and cheaper amplifier to provide a device for other use cases in the non-medical field. And Anouk created this Unicorn for children with ADHD. And the idea was that whenever something triggers the attention of a child, the camera in this Unicorn is turned on, and the camera is recording whatever caught the attraction of the child. And that's where we actually started the whole hard and software development for the more user-oriented tools. The Unicorn is also the device we use most for our Hackathon series. That's where we explored different use cases for BCI in a non-medical field and built small projects, and just had a lot of fun traveling around and creating small projects using BCI. And here's a small overview for the Unicorn suite environment. So I've showed you mainly the hardware environment of the Unicorn system, and this is the software environment. We have the Unicorn recorder, which is basically a tool to record data. So you can visualize EEG data, record data, and then do offline analysis afterwards. Then we have a couple of different APIs, for instance, the C API or the .NET API. So if you want to build a C application or a C# application, you can get raw data using these APIs. We have a band power tool, so that's a little more high level. With the low level APIs, you can get the raw data. With the band power tool, for instance, you can already receive a feature in your application, a band power feature. We have a UDP and a lab streaming layer interface. So if you don't want to use our tools, you can also use the Unicorn LSL, for instance, and stream data into your frameworks that you want to use, which is supporting lab streaming layer, for instance, OpenVibe or similar. We have Stellar, which is basically a P300 application. So we use that one quite often in the hackathon. P300 is a paradigm where you have to focus your attention to select something with your brain, and you can trigger actions of different software or hardware devices using that tool. We have the Unicorn Blondie check. So this is a neuromarketing application. Basically ranks images if they are triggering attention in your brain. So you're presented with a lot of different images, and afterwards, you can see which images triggered attention in your brain and which did not. And then we have some APIs for research interfaces like Simulink. Simulink is a drag and drop editor where you can build signal processing pipelines easily. So we use that a lot for prototyping real-time signal processing. We have a Python API, so you can also receive raw data within Python. And we have a Unity interface that you will also see later on when my colleague Bernard and Michele presenting the Unity stuff. And besides the tools that we provide within the Unicorn suite, we have a lot of interfaces on our GitHub. So you can check our GitHub there, and there you will find, for instance, a Linux API there, an API for Raspberry Pi, or the Bluetooth API documentation. So if you're not happy with our tools, you can also build your own API based on this. You will find some mechanical hardware drawings for the Unicorn native, and some of the software tools are also open source, like the UDP or the lab streaming layer interface or a Unity raw data interface. And here's again a small summary of different areas where we work together. As mentioned before, we work with digital artists. Most of our customers are researchers and developers. They want to build their own software, and with the APIs, they can do that. One of the latest additions to the Unicorn suite is the gaming interface. So we built the Unity interface so you can operate the BCI within the Unity environment. And we have a lot of tools for students and research labs. They often want to integrate it into their classes with large amounts of students and BCIs, and therefore we have this education kit where you can get 8 devices at once with all the software modules, all the research modules, and you can start research with your class right away. And this is one of the projects that we've been working on for the past month. This is the Unicorn Headband. This is the idea is to create again a more simpler version that you can easily integrate to your applications. And you can see I'm already wearing the headband right now because we're going to make a short live demo in a couple of minutes. And for the Unicorn Headband, we have 4 electrodes. You can see that they are placed over the visual cortex because right now we're using it for visual T300 experiments, for instance. And for this amplifier, we also have a 24-bit resolution, so we can measure small currents in a microvolt range. We have a sampling rate of 250 hertz, and to get a good signal quality, we need some strategies like oversampling and similar. And the Unicorn Headband is based on Bluetooth 5. So Bluetooth 5 is the low energy standard, so we can get to different operating systems using Bluetooth 5, like iOS, Android, Windows, Linux, and Mac. And that's what we are currently developing. So here you can see a little more detailed view of the Unicorn Headband. You can see the 4 electrodes on the visual cortex, and you can see that you just plug the amplifier with a magnetic sock on the base station, and that's how you turn the device on, and that's how you can start your development. And if you want to turn the device off or transport the device, you just flip it around, and you can transport it with this magnetic sock as well. And now for the hackathon, I want to give a very short introduction of what we are able to measure and what we are measuring with the Unicorn and so on. So there are in general a couple of different BCIs, invasive BCIs, where you're measuring within the brain, like ECOG, we're placing grids in between the skull and the brain, or spike electrodes that range into the brain. But that's nothing we will do for the hackathon, because that's just possible in a medical environment. What we're doing is non-invasive EEG. So we're measuring outside of the brain on the surface of the skin. And we can measure with dry electrodes there. We can measure with gel, or with the Unicorn, we can do both within one electrode. So we have this hybrid electrode. You can see what the signals would look like for the different technologies. And there's another technology called the fNIRS. The previous methods, they're all based on measuring currents and voltages. And the fNIRS is measuring blood oxygenation. So the blood vessels have oxygen, are transporting oxygen, and we can measure the oxygen level by with some light sensors, and that's called fNIRS. So for the hackathon, we're mainly focusing on the non-invasive EEG signals. And typically, this is what some EEG signals would look like in a time scale and in a frequency range. So on a time level, you can see most of the signals are within plus minus 20 microvolts. And in the frequency range, we're mostly interested in the frequency range within 0.5 to 50 hertz. That's where we have most of the EEG signals that we can use for surface EEG. And therefore, we also have to do some pre-processing, because there are a lot of artifacts within this frequency range and within the whole frequency range that we are acquiring. And since I mentioned we're mostly interested in the frequency range of 0.5 to 50 hertz, we can remove all the other frequency ranges and add some additional notch filters to remove the power line hum. So that's the default pre-processing for EEG. And then we can do different things. For instance, we can measure frequency bands. So we might want to be interested in frequency bands if we want to measure focus or some task-related frequency band changes. Or for sleep EEG, I guess most of the people know that there are different frequency bands, like the delta band, which is a very low frequency band, ranging from 1 to 4 hertz. You will find these signals mainly in deep sleep. The theta band is you will measure that in a transition in between sleep and awakeness, or in a very relaxed state. Then we have the alpha band. The alpha band is mostly triggered on the visual cortex as soon as you close your eyes, because then the neurons at the back of your head on the visual cortex are synchronizing, and we will find a peak at a frequency range of 10 hertz, and that's very significant. You can also see that on the right-hand side. You can see a frequency plot there, and the blue line is when the subject had the eyes open. So the frequency band looks a bit different compared to the frequency band when the subject closed the eyes. Then you see this 10 hertz peak rising. And that's something that you could use, for instance, within the BCI application, for instance, in the hackathon, to control the BCI by putting the brain into two different states and looking for this peak in the 10 hertz frequency range. And then there's beta and gamma bands, and this is like more focus and very specific focus. So the more alert you are, then higher the frequency becomes. And another type of paradigm that we use often are visual evoked potentials. There are a couple of different types. So if you have a stimulus blinking a couple of times, then we're measuring VEPs or P300. And you can see that on the right-hand side. So that's a single stimulus. You have the flash, and whenever something is flashing, you're triggering a signal on the visual cortex at the back of the head. And this is called the P300 or the VP. So you can perceive the blink. The signals are transferred via the optic nerve to the visual cortex, and then you have some specific pattern on the visual cortex that you can measure with some EEG device. And if you don't have a single blink, you're having a more regular blink with a frequency, then we're talking about SSVP. So as soon as the blinking is faster than around 6 Hertz, we can measure SSVP. And for SSVP, we have the blinking, and we're looking for the exact same frequency in the EEG signal. And if we can measure that, then we can control something with the BCI. And then we have the third type of visual evoked potential, which is called CVP, code-based visual evoked potential. In this case, we have a code flashing, and we're looking to decode this code again from the EEG signals. That's called CVP. And we're using this visual evoked potential for the Blondie check, for instance. This is the neuromarketing application. Here you can see that there are a couple of different images flashing. And there's one image with a blonde lady. And on the right-hand side, you can see the signals that are triggered with this paradigm. So your brain is trained to detect faces. And whenever the blonde lady is appearing, some attention is triggered in your brain. This is called the P300 or VP, because you can see that there's clearly a peak, and that's meaning that you're paying attention to something. So that's a signal that we can use and collect with the Unicorn system, for instance. So I'm done with my theoretical part, and now we're coming to the more practical part of the presentation. And therefore, I'll ask my colleague Leo to pass by. It's going to be my subject for today. Or maybe we start with the Unicorn Headband first, and then we're doing the experiment with Leo. So, as mentioned before, we're working on this headband, and I already wear the headband right now. And here you can see the amplifier. To start the PCI, I just place the amplifier on my head. And then I prepared a small Simulink model to visualize EEG data. And what I'm doing right now is, as mentioned before in the presentation, I'm pre-processing EEG with a 50 Hertz notch filter, because I want to remove the power line hum, 60 Hertz notch filter, if I would use it in the US. And then we have a bandpass filter where I'm cutting the signals from 0.5 to 30 Hertz. I'm using dry electrodes right now, so I might want to go from 2 to 30 Hertz, for instance. Then I'm running the model. And we can see signals coming in. I want to just visualize the 4 channels that I'm acquiring. And we can see some good looking EEG data. I can also do some tests, like clenching my teeth a couple of times. That's how I would introduce some artifacts or move my head a little bit. Then I can also introduce some artifacts because right now I'm measuring with dry electrodes. And then I can wait until the EEG becomes clean again. And I can try to close my eyes for a couple of seconds. We can see some small alpha because I don't have much alpha signals. I'm a bit nervous right now. But as you can see, we can measure time series signals and frequency spectrum in real time with this headband. And right now I'm wearing it with 4 electrodes over my visual cortex. All right. So this was a short demo for the Unicorn device. I think my screen stopped sharing. I hope you can see it again. All right. So now I'd like to show you some more advanced applications. I'd like to show you the Unicorn system because that's what most people will use for the hackathon. And I'm going to apply it on my colleague, Leo. And I'm going to give you some comments while applying PCI to my colleague. So I just opened the Unicorn suite. This is the software framework that we use on Windows systems for the Unicorn environment. And first of all, I'd like to show you the same demo that I did in Simulink right now using the Unicorn recorder. The Unicorn recorder, we can visualize ET data, we can apply simple pre-processing to the EEG, and therefore I first turn on the device and open the recorder application. So first of all, I'm removing all the filters and start some EEG recording. And right now there's no useful EEG data yet because I'm just applying the BCI to Leo. Then I add the ground at the reference electrode. So I put 2 sticky electrodes at the mastoideus. That's the location where very little electrical signals. And that's where we measure the EEG in a reference tube. Oh. Recording stop. On it. Maybe you can get a little closer to the PC. So right now we don't see much at all because we didn't apply any filters yet. And that's why we need some pre-processing filters. So as mentioned before, most of the EEG signal is within plus minus 20 microvolts. And to measure the signals properly, we need to apply some filters. I'd first apply a bandpass filter to remove all the frequencies from 1 to 30 hertz, for instance. And now you can see that the signals are floating down and they they are located around 0 volts, but you can see that there is a lot of noise, and that's the power line hum that we can still see here. To remove the power line hum, we can add another filter, a notch filter. In Europe, we can add a 50 hertz notch filter. In the US, you would use a 60 hertz notch filter. You can also apply both, and we could also apply a cascading notch filter, which is useful for dry applications because you also see multiples of the 50 hertz or 60 hertz in your EEG frequency spectrum. So right now I'm going to add a cascading 50 hertz notch filter, and you can see immediately that the signal looks way more clean, and that's looking like good EEG. And now we can make some tests again. So Leo, can you clench your teeth a couple of times? Now we can see teeth clenches. Can you blink a couple of times? Now we can see some eye blinks, especially on the channels close to the eyes, on the forehead. The first channel has the biggest amplitude, and that's an artifact. We usually don't want to have that in our EEG. You can roll your eyes a bit. Now you can see some EOG, like some electrical potentials added to the signal by your eyes. And now we can measure some real EEG. So these the signals that you've seen right now are mainly artifacts. And now you can close your eyes for about 10 seconds. And now we can see some low frequency and high amplitude signals with a frequency range of 10 hertz. And that's some real EEG data. That's that these are alpha waves. So Leo is very relaxed. So we have to give him a task soon. And right now we recorded dry EEG. And you can see I can easily disturb this. So that's why you usually use dry EEG when you're alone and not moving much, because otherwise the EEG looks messed up pretty quickly. And I'm going to add some gel right now because I'll be moving around Leo a bit. And we can see the EEG in parallel. So right now I'm putting some gel into my syringe. And I'm going to add some gel to the first 4 electrodes. And we're going to wait till the signal becomes good. So now you can see the first electrodes are pretty stable. And if I move around the side, the first electrodes are not disturbed, just the electrodes in the back. And that's the influence of the gel. So with gel, you just get a better connection in between this, the skin and the electrode. And therefore, we can measure some more clean EEG. And right now I'm preparing the last 4 electrodes as well. All right. Now we should have good EEG on all electrodes. Let's wait until the signal settles. And now I can move around and the EEG is not disturbed anymore. And we have some good EEG to work with. So I'll stop the Unicorn recorder. Yeah, maybe also a small comment. On the right-hand side, you can see the signal quality scope. So right now we have good EEG on all channels, and we should be fine to do some BCI paradigms. Leo is closing his eyes again, and we can see some big alpha waves. So this is what you usually do before an BCI experiment. You check your signal quality, you check if the EEG looks fine, and if that's all good, you can start with some BCI experiment. And first, I'd like to show you the Blondie check, which is a P300 application that I showed before in the slides. This is the image ranking application. And this application is measuring the P300s, and we can test if we can get some good P300 signals. So you can see the paradigm here. We have 2, 3, 4, 8, 11 non-target images, which are just grayscale images, and 1 image with a blonde lady. And we expect this blonde lady to trigger attention in Leo's brain. And we can follow this system if it can detect it. So we're setting everything as default. And then we can start the calibration. So right now, images are flashing, and Leo is just looking at the screen. And whenever a face appears, triggering attention in the brain, and we try to measure that. And we made a study a while ago to where we just use colors and other images and faces. And faces are especially interesting for the brain. So we've seen if we're using faces for P300 spellers, the speller becomes more accurate. And this is because your brain is kind of trained to detect faces. The training will last about 1.5 minutes in this case. Then we can get some results from the system. So in this case, Leo doesn't have any mental task. He's just looking at the screen. And now we can test the system and test if it's very accurate or not. We can also look at the visually evoked potentials that we measured. And now we set the system to 10 flashes, and we can measure if Leo can select it with his brain. So we measured in the cross-validation that we can detect that perfectly. And within a couple of repetitions, we should be able to reach 100% accuracy with the system. And now we can do some ranking and see if that is really working. So if we can really detect what's triggering attention in Leo's brain. According to the cross-validations, we had around 5 repetitions for 100%. So we will set that. Now Leo is looking again just at the screen, and we can see if the blonde lady is ranked to the first place as we would estimate. Not really right now. So if it's not working, you would either increase the number of repetitions or redo the training and see if the system is fitting. We wait again to have some good signals, and we can start again. So it's more closer to the front, and we'd have to repeat the training to get a better classifier. So the next application I'd like to show is one that we designed with the Unity interface. So this game is called Brain Buddy, and the idea was to create the game for impaired children. And in this game, we're also using the visual evoked potential, and Leo has to control the keyboard and the BCI, and only if he is able to do both at the same time, he's able to control the game. So we have some good EEG signals, and Leo has to focus on the green dot in the middle of the game. And after a minute of training, we get a calibration result, and we can check if he's able to use the BCI system. And later in the game, Leo can change the game environment with his brain, and he has to control the avatar with his fingers and the keyboard. And if he's able to do both at the same time, then he's able to complete the game. So we got a bad classifier. Let's redo the training. Looks like Leo is still sleeping. Ah, yeah, start flashing. Still not good. Maybe let's give it a third try. If Leo is not able to control this P3 at the moment, and we're going to the APIs. Yeah, now we got a good classifier. So right now, Leo has to look at the green dot. So relax, focus for a couple of seconds. And not working at the moment. So Leo is not able to focus well. Maybe we'll focus on the second dot. Yeah, now he was able to focus, and he was able to move to the next dot. And the better you can focus, the better you can control the game. Right now he focused on the second dot. Third dot, and so on. And only if you can focus well and control the keyboard in parallel, you're able to complete the game. Now everything you're stuck in the middle of. So focus on this one. Yeah. Now move and focus on the one between the cherries. Yes, exactly. And so on. So you can see if Leo is able to focus well, he can change the environment by will pretty well. If he's not able to focus well, then it doesn't work that well. Now you're stuck again. So I think Leo is a bit sleepy for these applications at the moment. But I hope you got the idea what you can do with this interface. Yes. Now you got it. Exactly. So you can always see when we are able to detect that he's focusing on something, then the white circle appears. And when we select it, then this blinkery animations come out. And that's what you can do, for instance, with a BCI within a game if you're using the event-related potentials. So Leo is almost completed, has almost completed the game. Just one more selection. Yes. Go, go, go. Yes. Last selection. So typically with some good EG signals, and if you can focus well, you can select items within 2 to 4 seconds. Yes. Yes, exactly. That was the last item. So for Leo, it took, I'd say, around 6 seconds. So if you're not focusing well, then it's harder for you to select something. If you can focus well, then the system becomes faster. So I've showed you 3 of the applications right now, the recorder, the Blondie check, and the brain body game. We have about 20 minutes left, so I'm going to show you the band power application as well. So right now you've seen how to check the signal quality with the Unicorn recorder. In the Unicorn recorder, you can also record data and send a trigger to Unicorn recorder. So you could record some data that you want to use for offline processing, for instance. And you can also stream the data via lab streaming layer. So you can use Unicorn recorder, pre-process your data, and stream data out via lab streaming layer, for instance. Or if you want to run a paradigm, you create your flashing, beeping, or whatever, send the trigger to Unicorn recorder, and receive the data with synchronized trigger in your own application. With the Blondie check, you could do some image rankings, and the brain body is just a demo game what you could build from the Unity interface. The next application I'd like to show is the Unicorn band power. And the Unicorn band power is some feature extraction tool. As mentioned before, there are different frequency bands, and with the Unicorn band power, you can measure all of them. So you can see right now Leo closed his eyes and the alpha band immediately rises, and as he opens the eyes, the alpha band drops again. On the bottom channel, you can see all the frequency bands ranging delta, theta, alpha, beta, and gamma. And you can see all the 8 channels. Right now, Leo has very big alpha waves, and alpha was most present. he opened his eyes and alpha went away. We can also check the average. So right now we have no alpha. So Leo, can you close your eyes? And we can see alpha band is rising and becoming the most present frequency band. And that's what you can do with the band power application. You could also go to sleep and check if theta and delta waves are rising. You could do some math tests and check if the beta and gamma bands are rising. So band power is a feature that a lot of neurofeedback tools are using. You could average sections of the signal and calculate the mean, check if you can trigger a raise or a falling in a specific frequency band. You can measure some biomarkers like alpha theta ratio or beta gamma ratio or whatever band power based biomarker you want to acquire. And you can not only visualize data within this tool, you can also stream data out. And therefore we have a UDP interface. You can set the network settings in here. And if UDP is enabled, you can receive data via UDP. And if you've finished with your setup, you just go back to the main dialog and you can record and stream data. You can see that there's this Wi-Fi item on the top right that indicates if you're streaming data or not. You can also record band power data by pressing the record button. Then whatever you see in the UI is also written to a CSV file. All right. Yeah, if you have a bad signal for some reason on one channel, you can also remove EEG signals in here. Then only the couple of channels that you want to use are displayed. Like you might want to use the front channel if you don't want to have eye blinks. Like right now, Leo is blinking. You can see the eye blinks on the first channel. And if he clicks the first channel again, then this channel is gone and the other channels are not affected that much. So you might want to use that feature as well. All right. So now I've showed you the Unicorn recorder, the band power tool, the brain body, and the blondie check. The Unicorn speller can be used if you want to implement the P300 paradigm in your application. I'm skipping that demo right now because we just have 20 minutes left, but I can show you the software shortly to give you an idea what you can build with that software. So in this case, you could use the P300 signal to select letters or numbers from this matrix and select it with the DCI. And if you select it, you can send the selection command via UDP to your own application. So in this case, you would see letters and you could use to write, but you can also modify the board matrix and create your own board matrix that could look like a robotic control, for instance. We have a demo for this here because we also have a painting application. And now you could select one of these items for your application. And you can configure the network output for each of these items in the board and timing section. We have each item, the image, the dark image, the name, and all this information is sent via network. So whenever something is selected, you could receive that in your application and control something. To give you some better idea how that would look like, I'm opening the painting as well. This would be an example how you could use this network output from the Unicorn speller to control something in the painting. So we would connect this application via UDP to the Unicorn speller, and then we could simulate a BCI selection, like turning the item to red. Then the item turns red, or we can move it left, then it would move left. So I hope you get an idea how you could use the Unicorn speller to control your own software. And you can see I just typed left and red, and this is exactly what we've defined here. We had the board items with the image on the speller, and whatever I sent via network right now was a simulated output like red or left and so on. So if you need some more information, what you could do with this interface, we also have tutorials on our GitHub. So I'm also showing you that shortly, because the whole manual and software tutorials, etc., they are all on our GitHub. And you might want to use that for the hackathon. So we have the Unicorn Suite Hybrid Black repository, and here you will find all the software tutorials that are on YouTube. So if you want to get an idea for the capabilities of the speller, for instance, you just click the speller video and you will find the YouTube tutorial. And we have software tutorials for all the software that we support at the moment. And also the manual of the Unicorn is on our GitHub. So I ask you to please check the manual first, because most of the software should be documented there, and you will should find some information there. So here's the software manual. So whatever software you want to use, like for instance, you want to use the band power tool, then you will find a section for the capabilities of the band power here, like how the UDP package would be structured if you send it, how the CSV file is structured if you record data, and so on. And these were the applications. And finally, I'd also like to show you some tools for the developers shortly, because I guess some people will also like to play around with raw data or something like that. And in this case, you could use some of the APIs. So we have a C API and a .NET API, and maybe opening one of these shortly. You will always find a lib folder, and in the lib folder, there are the binaries that you will need to integrate into your application. And you will always find an example, and the example just shows you how to set up a data acquisition. And to give you an idea how data acquisition usually looks like, I'm now opening the C# API. There's an introduction how you set up your project and how this acquisition example usually looks like. So for a PCI system, we are getting continuously data with a fixed sampling rate, like the Unicorn sends you 250 samples in a second. And therefore, we need something like, we call it an acquisition loop. So we usually connect to our device, then we start data acquisition, and then we're acquiring data in a loop for the amount of time we want to receive data. And when we're done, we're finished. And in the meantime, the C# API should have loaded. I can try to build it and give you a short idea how this acquisition loop would look like in code. So maybe we can put it aside. So we have the get available devices. Yeah, everything's built. Good. Let's make some space so you can see what I'm looking at. So first of all, we want to acquire the available devices. Therefore, we call get available devices. That's the first section. Then we open our device. That would be the opening command, which is there. We get create a new instance of the Unicorn class. That's the device. Then we enter a loop. And in this time, this loop is a for loop. So we defined how long we want to record data. In this case, I think we set 10 seconds. Yeah, we've set 10 seconds. And in this loop, we're calling the get data continuously. And when we're done, we stop the data acquisition and we're closing the device. So this short code example represents the image on the right-hand side. And that's what you would probably like to integrate in your application if you want to use one of the APIs. They're all following the same principle. So no matter if you're using the C#, the C, or the Python API, they are all integrating this same strategy. And just to show you how that would look like, we're checking for available devices, then connecting to the device. In the loop, we're measuring data and receiving data all the time. And after 10 seconds, as we've said, the data acquisition is stopped again, and we're disconnected from the Unicorn. So exactly as mentioned in the image, get available devices, open device, start acquisition, looping, stopping, and closing the device. And that's the basic strategy for all the BCI systems if you want to get raw data in a data acquisition system. So no matter if you're using the C API, the Python API, or the C# API, they are all following the same strategy. I've already showed the Simulink shortly with my Headband demo before. So in Simulink, you have these nodes that you can just drag and drop and connect. So that's more a visual programming for real-time applications. Like when you want to test your own algorithms or something like that, that could be something that you might want to use. And then we're having the lab streaming layer and the UDP interfaces. They are also programming interface, but with a small GUI. So for lab streaming layer, we just have a very simple GUI that is sending all your signals from the Unicorn to lab streaming layer. And lab streaming layer is a standardized network protocol. So if you're sending data via lab streaming layer, you could receive it in another application. And I've also added a receiving example on our GitHub, or there's also one installed in with the recorder. Maybe I can also show that shortly. And I think then I'm done with the time already. The Unity interface will be presented by Bernard and Michaela later on. That's the last tool that we would have in the development tool section. Maybe while this loading, I can also show you shortly. We can hand out some licenses for the hackathons, please just give me your email so we can deactivate them afterwards. And we have this My Unicorn section. So in here, you can see if everything is set up properly in your PC. And here you can see right now, I didn't set up Bluetooth correctly. So that might be also a reason why the demo didn't work that fast previously. So in best case, you want to have all the sections turning green, because then that's what we've tested to be most reliable for the configuration. So I think the demo is loaded. We can run it. I'm missing a file, but it can be get easily. I'll update the installer in a minute because I've seen I've missed the file here, but we're done with that quickly. So here's the UDP receiving example. And you can see the stream from Leo already popped up. So the Unicorn LSL is streaming, and in here you can receive data continuously in the data stream for all the 8 channels. In general, the Unicorn is sending 17 channels, 8 channels of EEG, 3 channels of accelerometer, 3 channels from a gyroscope, a battery level, and a validation indicator, and a counter. Yeah, you can also use that one to stream into your own application, into HYSYS, for instance, or into some other framework that is supporting lab streaming layer. If I stop now, also the stream stops. And yeah, I think
Thank you very much, Martin. There are a couple of questions. Nana is asking how much in the Blondie check. So how much influence does the lightning of the images have?
I think that like all of these things have influences, because what we've seen so far is if you're training on a specific type of pictures, that you should also apply it to a similar one. Like we've seen what works best is like with train to grayscale versus colored images. That works well, but then we should also use that in the application. Or if we train to faces that we know versus we don't know, we also have to train the system to that one. So if you want to get a reliable classifier and a good performance, you would like to have similar kinds of picture set, but it would work also to have some colored images and one very bright one and other ones are dark. It would also trigger P300.
Then Martin is asking, what's the reference electrode in the Unicorn Headband?
For the headband, we have 4 channels in the back, and on the side of the head, we have a 5th electrode, and that's the reference electrode close to the ear, because that's where for most of the EEG signals we see in literature, the reference electrode is at the ear or the mastoideus. So we also choose a close location.
Then somebody's asking, how can I install the Unicorn suite?
For the hackathon, I created a repository that is not public at the moment, but as soon as the hackathon starts, it will be, and you will find the beta version of the Unicorn suite there.
Then somebody's asking about the LSL and UDP interface. Martin showed it. And there's also a video on GitHub, so you can watch how to configure LSL and UDP again. Then can you please share the GitHub link when are people getting the GitHub link?
Yes. As soon as the hackathon starts, I'll make the repository public and I'll post the link on the Discord channel.
Then somebody is saying, I'm not able to find the Excel file for Unicorn Suite. I do have a license, but it's not available from the website GitHub as far as I checked.
Yeah, it's not public yet, but the download link will be there, and you have a setup extra that installs the whole Unicorn Suite.
How can we achieve 2 simultaneous Unicorn apps connections at the same time on one computer, I guess?
Yeah, like the Bluetooth is a bit limited, so I wouldn't recommend it to do on one PC, but 2 devices mostly work well. From 3 devices on, then Bluetooth is very likely to crash. But the best solution would be you have 2 PCs, and for instance, you take live streaming layer on both PCs and then stream to another application that is receiving from both live streaming layers, because then you can get the stable data connection on both PCs. Each one connects to one Unicorn, and you can merge the data streams in another application.
Sami is asking how to get the API and the licenses.
Yeah, again, that's with the GitHub link that will publish in some time before the hackathon starts.
Then somebody is saying, I applied for the hackathon, but I didn't get the acceptance email. Maybe you can drop your email here and then we can check if we received the email. And Martin is asking, can people already use the Oscar for the Unicorn in the hackathon?
There's a integration in the Unicorn recorder. You have this Oscar checkbox, so you can use the Oscar, and you could stream data to your own application, and Oscar is previously in the Unicorn recorder.
Then Gregory is asking if the Unicorn is the only system able to work with the brain computer interface. Maybe I can answer that. Of course, you can also use a HMB USB and a Nautilus Pro, a Unicorn Hybrid Black, a Unicorn Headband. So these are the devices that g.tec is producing. But if you got another EEG system, you're also welcome to use that. The demos are done, of course, with our hardware because we have it fully under control. And Baram sent the email, so we will check if we got your registration and will reply to you. Thank you very much, Martin and Leo.